Good evening, everyone. Thank you so much for taking your valuable time for attending this session. First of all, I would like to thank Michael Anderson for giving me this wonderful opportunity to speak for Glass user group. So my name is Deepthi Goguri, and today I would like to present on the topic SQL Engine and its working style. So basically, this session is all about SQL Server internals and architecture. So there is a lot of content to grab. Hopefully you like it. Let's get started. A little bit about me. I'm a database administrator with 7 years of experience in managing SQL Server and databases. I'm a Microsoft certified trainer and Microsoft certified solution expert. I did my master's in computer technology at Eastern Illinois University. I blog for dbanuggets.com. That's my website. And you can contact me on Twitter at dbanuggets. That's my user ID. And you can contact me through email. That's my email address. If you have any questions regarding this session, please do not hesitate to contact me. So what are we going to go through in this session today? We are going to see the overview of ACID properties of transaction with a very simple example ensuring the ACID properties. We are also going to go through the different types of components we have in the memory architecture of SQL Server. In this session, we are going in deep into the bigger components of the memory architecture of SQL Server, which is the plan cache and the buffer pool, and how these cache get managed inside the SQL engine. And we are also going to go through the life cycle of a query for the read as well as the write transaction. That means like what happens behind the scenes at each component inside the SQL engine. We are also going to see the different types of components we have in the SQL engine, that's relational engine as well as the storage engine. So internals, why should we actually care? Many DBAs and developers, they work with SQL Server on daily basis, but might not exactly understand what happens behind the scenes when we submit any query to the SQL Server. So knowing this information will help you in understanding how queries are processed at each step inside the SQL engine. It will also help you in tracking down the performance issues very quickly and fix them efficiently. It will also build you confidence while managing the SQL engine as well as the databases. It will also help you in convincing your coworkers or managers of why they have to take your ideas seriously. Last but not least, we work with SQL Server every day. So the more we understand about the internals, the better we can manage the SQL engine as well as the databases. Let's start with basics, the ACID properties. So every major relational engine, it can be the SQL Server, Oracle, PostgreSQL, Sybase. All these major relational engines should satisfy the ACID properties of transaction. What is this ACID? A stands for atomicity. Atomic meaning a single unit of work. A single transaction can contain one operation or it can contain multiple operations in it. Each and every operation inside the single transaction should complete successfully or none of them. For example, we have a store procedure, and inside the store procedure, we have two operations in it, the update statement as well as an insert statement in it. Whenever you execute the store procedure, both the operations should either complete successfully or none of them. For example, if the update succeeds and if the insert fails, then SQL Server should go ahead and roll back the entire transaction. That's atomicity. C stands for consistency. Data inside the database should always be consistent before starting the transaction and after completing the transaction. For example, if I wanted to do an update statement onto a table, and while I am doing that update, if something happens suddenly, like if there is a power outage and we had to restart the SQL Server, once we start the SQL Server, all these uncommitted transactions should be completely rolled back, making the data in the consistent state. That's consistency. I stands for isolation. No matter how many concurrent transactions are happening at the same time, each and every individual transaction should be independent of each other without interfering with any other transaction. For example, I am inserting few rows into a table. So while I'm doing that insert, none of the other transactions should be interfering with my transaction. That's isolation. D stands for durability. Once the transaction is successfully completed and all the data has already been made to the database should be permanent. That means if I had to restart the SQL Server later anytime, all the transaction which is already committed, the data which has already been made to the database should be permanent and it should not be any data loss. That's durability. So what components of this SQL engine will ensure the ACID property? Atomicity is very easy to be ensured. It is taken care by the parse component inside the relational engine. Consistency is also very easy to be ensured. It is taken care by the parser and binder components inside the relational engine. Once the atomicity, isolation, and durability are ensured, consistency will automatically be ensured. Isolation is all about the locking mechanism. It is taken care by the lock manager inside the storage engine. Durability is the most toughest of all. It is taken care by the transaction log inside the storage engine. Let's see a very simple example ensuring the ACID properties of transactions. For example, we wanted to take a simple bank transaction here. For example, I have a balance of $500 in my account, which is of ID 1, and I would like to send $100 to my friend's account, which is of ID 2. I can do this simple bank transaction multiple ways, right? I can use the online bank application, or even I can use the mobile phone application to do it. I have a bank application on my phone to do this. So in this example, we are using the mobile phone application to do it. So once we begin the transaction, SQL Server will also begin the transaction on the background, right? This particular transaction has two operations in it. First operation is to deduct $100 from my balance, and the second operation is to credit $100 to my friend's account. So once I begin the transaction on my mobile phone application, SQL Server on the background, it will begin the transaction. It will go ahead and deduct $100 from my balance, where ID is 1, which will make of $400. This is the operation number 1. And the operation number 2 should be crediting $100 to my friend's account. But I suddenly see this on my screen. I am logged out of the mobile phone application and I see this alert saying facility is temporarily unavailable. Now wait, what? What has happened? I'm in between the transaction. My transaction is not completed yet. I do not know if I lost my $100 or if my friend has received $100. So I called her to ask if she received any money, which she said she didn't. So I have no other option except calling the customer service guys. So when I called them, they said there was a severe thunderstorm and some of their SQL Server went down and they had to restart the SQL Server. So once they restart the SQL Server, what should happen? If this particular transaction ensures the ACID properties of transaction, what should happen? Just think. Let's see what will happen once they restart the SQL Server. Once they restarted the SQL Server, all these uncommitted transaction is rolled back. So this particular transaction is ensuring the ACID properties of transactions. Now how? Atomicity is ensured by rolling back the entire transaction. Consistency is ensured by reflecting $500 in my balance, which is the initial amount before starting the transaction. So consistency is also ensured. Isolation is also ensured. Like, did you observe when the SQL Server went ahead and deduct $100 from my balance? None of the other transactions were interfering with my transaction. Isolation is also ensured. The durability part is also ensured. I do not lose my money. I have my $100 back into my balance, which reflects $500, which is the initial amount before starting the transaction. And transaction log made this possible once the SQL Server restarted. So that's how all the major relational engines should satisfy each and every transaction for this ACID properties of transactions. So let's see the overview of SQL Server memory architecture. SQL Server Engine is a Windows program which will use Windows APIs to allocate memory to the SQL Server. So there are different types of components we have in the memory architecture of SQL Server. In this session, we are going to mainly focus on plan cache and the buffer pool because these are the major components. But let's see what other components we have in the SQL Server memory architecture. Firstly, the plan cache, which is one of the major components. It holds the store procedures, query plans, etc. And the buffer pool, it holds the 8 KB data pages and the index pages. This is the biggest component inside the memory architecture of SQL Server. There are also other types of cache, like for example, the log cache, token and perm user store cache. Now what this token and perm user store cache does is it will store the user permissions onto the objects. Now there is also other type of cache which is known as column store cache. which will store the column store indexes in it. Now, all these caches which you are seeing in the blue color are very special. Now, they are very special because they have a backing mechanism in them. They can be easily expanded and shrinked when there is a memory pressure. Now, how? Because there is a backing mechanism in them. For example, the plan cache, which holds the store procedures, the query text of the store procedure, it is stored inside the system tables. The buffer pool, which stores the 8 KB data pages, it is stored as the database files on the disk subsystem. The other caches, like the log cache, it is stored as the transaction log inside our disk subsystem. The column store indexes, which are stored inside the column store cache, these column store indexes are compressed and also are stored inside the disk subsystem. Now, when there is a memory pressure, all these objects inside these caches will be pushed to their backing stores. But what about the fixed memory, which is in the green color? The fixed memory is known as fixed because it cannot be expanded or shrinked when there is a memory pressure. Now, now in the SQL Server, this fixed memory holds less than 1%. Now, what kind of things will be held in the fixed memory? Fixed memory holds connections to the SQL Server, like the memory grant connections. Memory grants to the hashes and sorts we use for the queries to be processed. Those kind of connections are stored inside this fixed memory. Now, this is known fixed because it doesn't have any backing mechanism in them. Now, what happens when this fixed memory is full, right? There is a mechanism in SQL Server which will be triggered whenever this fixed memory is full and request the caches which you are seeing in the blue color, which are the major components. The SQL Server will request these major components of memory architecture like plan cache and the buffer pool to release the objects and push them back to their storage systems, such that it will give some memory, so that memory, that freed up memory, will be used for the fixed memory for more connections. But the fixed memory can't just go ahead and disconnect the connections which are already made to the SQL Server, right? So it will request the other memory components to release the memory. So that's how the fixed memory gets managed. There is also other type of memory known as SQL Server.exe overhead memory. It stores as you know, the SQL Server.exe is an executable, and many things will be running this executable, right? Like for example, the thread stacks. Even this component will come under the memory architecture of SQL Server. Now there is other type of memory known as in-memory OLTP. Now in-memory OLTP holds the memory optimized tables, and even the in-memory OLTP is fixed memory. That means it cannot be shrinked or expanded when it is in use. There should be some other process which should kick in and clean up this in-memory OLTP such that it will have more space for the newer objects, newer memory optimized tables to fit in. So this is the overview of memory architecture. Now let's see how the plan cache and the buffer pool gets managed inside the SQL Server. Now there is something known as LRUK algorithm, which is known as least recently used algorithm. The -K is for the complexity of the code. Now what is this LRU? LRU meaning if something is staying in the cache for the longer time, those kind of things will be discarded first. But what happens with the SQL Server? SQL Server will think this way. If there is a execution plan, for example, if it got created with less amount of cost and resources, those kind of execution plan will be discarded first. But if it took so much of resources and cost to create that execution plan to be created and saved inside the plan cache, then those kind of plans will have more options to stay in the cache for the longer time. Now, how does this memory gets managed inside the SQL Server? There are two processes which will take care of these. One is the lazy writer and the other is the ghost cleanup. Now let's see how these process works for the plan cache. For example, we have a plan cache here. The right side diagram which you are seeing is my plan cache. It's really, really small. We just have 3 execution plans in it: the plan 1, plan 2, and plan 3. Now, for each and every object we have in the plan cache, we have 2 numbers at the bottom of each object. The left side number is known as complexity code value, and the right side number is known as complexity countdown value. Now, whenever the lazy writer kicks in every minute by the SQL Server automatically, what it does is it will go ahead and check if there are any least recently used execution plans. Now, in our example, none of them will be used. So what it does is it will go ahead and decrement the complexity countdown value by 1 on each object it thought it did not get used. Now, in our example, none of them will be used. So it will go ahead and decrement the plan 1 complexity countdown value from 18 to 17, for the plan 2 from 9 to 8, and for the plan 3 from 2 to 1. And the lazy writer will go away. In the very next minute, the lazy writer will kick back in again to see if there are any least recently used execution plans. In our example, none of them will be used again. So what it does is it will go ahead and decrement the plan 1 complexity countdown value from 17 to 16, for the plan 2 from 8 to 7, and for the plan 3 from 1 to 0. Now, did you observe the complexity countdown value for the plan 3 has changed to 0? That means the SQL Server should go ahead and discard this plan out of the cache, right? But that is not what it is going to happen. There is some other process known as ghost cleanup, which will be kicked in every few minutes by the SQL Server automatically. Now, what it does is it will go ahead and flag those execution plan which doesn't have any countdown value as ghosted. It will just go ahead and flag them as ghosted. That means they are still inside our plan cache, but they are in the half-life. Like for example, there is a memory pressure tomorrow, right? The fixed memory might be full and the SQL Server might request these plan cache to release the memory to push these objects out of the cache, right? In that scenario, what the ghost cleanup does is it will go ahead and clean up, it will just push away all these plan caches, all these execution plans, sorry, out of the cache. But if there is no memory pressure, the SQL Server will still going to keep these execution plans inside the cache, such that tomorrow some other user might come and use the same execution plan for his query. So that's how the ghost cleanup works. And in the very next minute, the lazy writer will kick back in again to see if there are any least recently used execution plans. In our example here, the plan 2 will get used. So what it does is the lazy writer will go ahead and increment that complexity countdown value from 7 for the plan 2 to its original value, which is 9. So that's how the lazy writer and ghost cleanup will manage the plan cache. Now let's see how the buffer pool gets managed. Buffer pool, it stores the 8 KB data pages and the index pages in it. So basically the buffer pool has to manage 3 types of different structures: the heaps, clustered indexes, and non-clustered indexes. For example, if you wanted to do a select star from a heap table, what will happen? You know what will happen. The buffer pool has to go and grab all these data pages into its buffer pool and do the operation over there, which is very IO intensive, right? To go into the disk subsystem and grab all those pages, it takes so much IO, it is very IO intensive and cost consuming. So instead of that, if you put a clustered index and non-clustered index on the top of that particular table, the buffer pool has to just go ahead and grab those index pages very few trips to grab those pages into the buffer pool, which helps reduce the IO and speed up the query process. Now, how does this buffer pool gets managed? There is something known as a checkpoint process, which will be kicked in every few minutes by the SQL Server automatically. Now, what it does is it will go ahead and check if there are any dirty pages inside the buffer pool. Now, what are these dirty pages? Dirty pages are the pages, the 8 KB pages, which are already modified in the buffer pool, but they are not hardened them yet into the disk file system. So what the checkpoint process does is it will go ahead and check if there are any dirty pages inside the buffer pool and push those dirty pages back into the database file system and harden them onto the disk. That's how the checkpoint process works. And if you want to run the checkpoint process manually, you can type the word checkpoint in your management studio. Whenever you execute it, the checkpoint will go ahead and push those dirty pages out of the buffer pool and harden them onto the database file system. That's how the checkpoint process will manage the buffer pool. Now, this is the very important slide. How SQL Optimizer will choose the plan. As you know, the SQL Optimizer is a cost-based optimizer. It always wanted to choose good enough plan instead of the best plan. Now, what is the difference? The time and the cost is the difference. For example, we have a very simple select statement here with a 4-table join in it. And on each table, we have a clustered index and 3 non-clustered indexes on each of the table. For example, if the optimizer wanted to choose the best plan instead of the good enough plan, what it have to do? It have to go ahead and analyze 72 different types of physical access method per table. That means we just have 4-table join here, right? It have to go ahead and analyze 72 times 4 physical access method per table for this simple select query. So what are these physical access methods? The optimizer have to go ahead and choose whether it have to do a clustered index scan or seek, or whether it have to use any covering index, those kind of things. 72 per table, it have to analyze. On the top of it, it have to go ahead and analyze 24 different types of logical join orders for this simple select query. Now, what are these logical join order? We have a 4-table join statement here, right? For example, if the join between A to B will filter out 60% of the records from the result set, and the join between B to C will filter out 90% of the records from the result set, then the optimizer wanted to go ahead and reorder the join in such a way that it will push the join between B to C front of the statement and the rest of the joins back of it. Now, why the optimizer do that is because it wanted to grab the results as quickly as possible. On the top of it, it have to go ahead and analyze so many transformation rules, at least some thousand of them, some thousands of them, and it will go ahead and analyze all these transformation rules and grab approximately 26,000 possible plans. Now just imagine how much time and resource consuming it is for the optimizer to go ahead and choose the best plan out of these 26,000 possible plans. First, it have to build all these 26,000 possible plans and grab the best one out of them. It takes so much of resources to do it, right? And no user wanted to wait for such long time to grab the results. That's the reason why the optimizer will go ahead and choose the good enough plan instead of the best plan. And how it do that is it will go ahead and analyze very quickly some of the transformation rules to get that good enough plan instead of going ahead and analyzing each and every transformation rule to get the best plan. And that's the reason the optimizer is so quick. I would like to thank Kevin Klein for loaning me this example. If I tell the concept in the very simple words, if for example, if the optimizer choose the execution plan A in 3 milliseconds and execution plan B in 3.5 milliseconds, and in order to know if the plan A is better or B is better, if it have to go ahead and analyze many transformation rules for at least for 5 minutes, then it doesn't want to do that. It will go ahead and grab the execution plan A or B randomly. That's the reason why the optimizer is so quick in getting those good enough plans. Let's talk about the life cycle of a query. So if the life cycle of a query is divided into 3 different steps, then the first step contains the components parser, binder, simplification, and trivial plan. Now all these components inside the first step are very simple, very lightweight to the SQL Server. It doesn't require much resources at all. It just requires the query definitions as well as the table definitions in it. That's all it needs. When you come to the second step contains the load metadata, join heuristics, and search phases. Now all these components inside the second step are they require most of the metadata to process any of the query. Now when you come to the third step contains the access method, transaction manager, and buffer manager. Now when you compare with the other 2 steps, the first step and second step, the third step is very IO intensive because the buffer manager component, it have to go ahead and grab the database pages and index pages into its buffer manager, buffer pool, which is very IO intensive, right? That's the reason it is cost consuming when you compare with the other 2 steps. Now, the first step components and the second step components will come under the relational engine, and the third step components will come under the storage engine. Now, let's see a very simple select query, how it runs behind the scenes when a user submit a query to the SQL Server. For example, we have a user here. No matter what kind of interface he is using, he can be using SQL Server Management Studio, Azure Data Studio, .NET Visual Studio, or even a third-party application. No matter what kind of interface he uses, first the user should get the secure network connection to the SQL Server, right? But how does that happen? There is something known as SQL Server Network Interface, which is also known as SNI. Now, what this SNI does is it will establish a secure network connection between the SQL Server as well as the client. The client is the user here. Now, how does the SNI do that? It will use the Internet Protocol to do that. Now we have different types of Internet protocols, right? The TCP/IP, named memory, shared memory, and named pipes. No matter what kind of internet protocol we use, the process remains the same. So once the secure network connection has been established between the SQL operating system as well as the user, the query that the user is sending will be wrapped inside a tabular data stream packet, which is also known as a TDS packet. Now this TDS packet will be given to the SQL operating system by the SNI. Now once the TDS packet has reached the SQL operating system, the SQL operating system, it will first identify that coming connection as a SQL connection, and it will assign a SPID to it. You know the SPID, right? The SQL process ID. Whenever you run the SP-who2 or SP-who, you see those SPIDs like SPID number 65, SPID number 95. Those SPIDs are the active connections which are made to the SQL Server. Now, once the SPID is assigned, the tabular data stream packet, which is at the SQL operating system, will be unwrapped at this phase, and that particular query is identified as the SQL query, and that query is now sent to the first step inside the relational engine, which is the parser. The parser is the first component inside the relational engine. So what this parser does is, parser will identify and validate the syntax of the query. For example, if you wanted to do a select star from a table, but by mistake you have given select star from, at this particular parser stage, the parser should identify that query as syntactical error, and it should throw back the error to the user saying it is syntactically incorrect. And also at the parser stage, the variables are declared. For example, the variables which you are using in the query, whether they are valid or not, those things are checked at the parser component. And views are expanded here. If at all you are using the views inside your query, then the query text behind that view is brought in line into the code we are sending. Basically, the views get expanded behind the scenes. With all this information, the query, what happens is the parser will put a hash on the query we are sending, and it will check against the hash of the execution plan inside the plan cache. If it finds the exact match, then it will go ahead and use the same execution plan from the plan cache to the execution phase. But what if there is no exact match? What if the query is running for the first time to generate the execution plan? Then at this particular parser component, the parser will build the initial logical tree at this phase, and then our query will be sent to the binder component. Now the binder component, also known as algebraizer or normalizer, what this binder does is it will go ahead and validate the objects that we are using in our query, whether they are valid or not, like the columns or tables, if they are valid or not. The parser will just identify the syntax, but the binder is the one which will identify and validate the objects we are using in our query. And check user permissions happens at this binder component, whether the user that running the query, whether he have the enough permissions to execute those objects or not. Those kind of things are checked here. Data type resolution also happens at the binder component. Now, for example, you wanted to do a select statement between two tables and you are using a union clause in between those two tables, the ordinal column of those two tables should match in their data type. Now I am going to show you an example of the data type resolution in our demo, but data type resolutions happens at the binder component. The aggregate binding also happens here. The sum, average, those kind of things are bound here. Now with all this information, the parse tree inside the plan cache will be once again updated, and then our query will be sent to the simplification component. Now the simplification component itself says it simplifies the query, right? For example, if you are running a select statement which have a subquery in it, then behind the scenes, the simplification component will go ahead and convert that subquery into a simple join. No matter how many times you run the query with the subqueries, behind the scenes, they are converted into simple joins. And the contradiction detection happens here, whether you have a foreign key contradiction, if you have any contradiction of those kind of things, they are identified at this point of time. And with all this information, the query tree, once again, it gets updated inside the plan cache, and our query is now sent to the trivial plan component. Now, what happens at the trivial plan component is, for example, we are running a very simple query, right? For example, the select star from a table or select star from a table with a simple where clause. Now, what SQL Server thinks is, this is such an easy query for me. Why should I even go ahead and update the parse tree that the previous component has been built? And why should I even go ahead and update that parse tree inside the plan cache? Let me go ahead and discard that parse tree which the other component has been built, and let me go ahead and create the trivial plan on the fly, because it doesn't cost it much. It doesn't cost any resources to create the trivial plans on the fly. So that's the reason why by default these trivial plans are not stored inside the plan cache. Now there is a reason why, because the SQL Server think, why should I even waste the memory inside the plan cache for these simple queries? Let me go ahead and use that same memory for the more complicated execution plans. Now, no matter um, how many times the user submit the simple queries of these kind, the SQL Server will go ahead and create the trivial plans those many times, because it doesn't cost it much. But what if, and then that particular trivial plan, if it gets generated, that trivial plan will be sent to the execution phase. But what if our query is not so easy? It is complicated with 10 tables in it, with a complicated logic in it, with order bys, group bys in it. Then that particular query will be treated as a little bit complicated query, and the SQL Server wanted to create the full plan for that particular query, and the query will be sent to the second step of the relational engine, which is the load metadata, which is the first component inside the second step. Now what it does is, most of the metadata that it requires to process any query are gathered here. Like for example, the index statistics and histograms. As you know, the index statistics, these statistics are the blob structures which are stored in the system tables, which describes the distribution of the data inside a column or set of columns or an indexed view of a table. And then these indexes will get gathered at this point of time. The optimizer will go ahead and analyze how many rows that it's gonna come back out of that particular table. And auto create statistics also happens here. Like if your auto create statistics option is turned on on your database level, which is by default it's turned on, then the optimizer will go ahead and create the auto create statistics on the column which we are frequently using for the searches. Like for example, if you are sending a select statement where you are searching on a column very frequently, and that particular column doesn't have any index on it, even then the SQL Server will go ahead and create this auto create statistics on that particular column. And SQL Server collation and Windows collation are checked here. Cardinality estimates are gathered here. The cardinality meaning How many rows does the optimizer think it is going to come back out of each operator inside the query tree? Those kind of things are gathered here. Set options are also checked here. Like for example, set XML on or off, set ANSI padding on or off. Depending upon on or off, the execution plan might be dependent. With all this information, the parse tree inside the plan cache is once again updated, and then our query will be sent to the join heuristic component. In our previous slides, I have discussed of what this logical join order is, but let me explain again. For example, we have a very simple three-table join statement, right? And the join between A to B may filter out 70% of the records from the result set, and the join between B to C will filter out around 99% of the records from the result set. Then the optimizer will go ahead and reorder the join in such a way that it will push back the join between B to C, front of the statement, and the join between A to B, back of it. Now, why the optimizer does is because it wanted to grab the results as quickly as possible. This all happens behind the scenes. And with this information, the parse tree inside the plan cache is once again updated, and then our query will be sent to the search phases. Now, in the very next slide, I'm going to discuss about what these search phases are. But just remember that we know that our SQL optimizer is a cost-based optimizer, right? It always wanted to choose the good enough plan instead of the best plan. Now, what the optimizer does is it will go ahead and grab the execution plan, the good enough execution plan from these three phases, phase 0, phase 1, and phase 2. Once it grabs the good enough plan, then it will go ahead and update those information inside the plan cache and put a hash on it finally. And then our query will be sent to the storage engine, which is the third step. But before going into the storage engine, let's see what these search phases are. Now, the SQL optimizer, no matter what kind of query we are sending to the SQL server, the optimizer has to go and grab the good enough plan from these three phases. The phase 0 is also known as transactional plan. All the execution plans are created at the pre-optimization stage. Now, what is this pre-optimization stage? The first step that we discussed, the parser, binder, simplification, trivial plan. These components comes under the pre-optimization stage. That means that most of the trivial plans are created at this phase 0. Now, these kind of execution plans are created very quickly at the phase 0. And these execution plans are created for very small queries with maximum of 3 tables, and very basic heuristics are needed, like the table definition, query definition. Those kind of basic heuristics are needed to generate these execution plans from the phase 0. When you come to the phase 1 is also known as quick plan. Now, these kind of execution plans from the phase 1 are generated for the queries for the maximum of 8 tables. More transformation rules are needed than the phase 0. Now, what happens with this phase 0 and phase 1 is the optimizer will take our query that we are sending, and it will go ahead and compare that query with already existing execution shapes. If it finds a good enough plan from those shapes, it will go ahead and grab the good enough plan from these phases. But what happens with the phase 2? Phase 2 is a little bit different. Phase 2 is known as full plan. Now, phase 2 execution plans are generated for the more complicated queries. The parallelism, spills, and spools to the TempDB happen at this phase. Almost all the transformation rules are unlocked here. Now, what the phase 2 does is the optimizer doesn't compare our query with already existing execution shapes, but instead what it does is it will go ahead and prune off all the transformation rules that we are not using in our query. Now, what I mean by that, for example, we are not using nvar max or blob data type structures, blob data types in our query. Then the optimizer will go ahead and prune off all those transformation rules which are related to the nvar max or blob data types, so that it can go ahead and analyze very quickly some of the transformation rules, such that it can get the good enough execution plan execution plan for that particular query. That's how the optimizer will go ahead and grab the execution plan from these three phases. Now our query is at the third step of storage engine. Now let's see the read transaction and then write transaction later. But before going into this storage engine, let me say that no matter what kind of query we are sending, it can be read, write transaction, no matter what kind of query it is, all the difference happens at this storage engine phase at the transaction manager and buffer manager. All the queries that we are sending to the SQL Server should pass through the first step as well as the second step based upon how complicated our query is. If our query is so simple, then it will then the trivial plan gets generated and it will be sent to the execution phase. But if it is a little bit complicated query, then it will pass through the second step and then through the third step. If it is a very simple query, then the trivial plan gets generated and sent to the storage engine. But all the difference happens at the storage engine at transaction manager component and buffer manager component. Now let's see for the read transaction what happens. The access methods component, what it does is it doesn't perform any operation by itself, but what it does is it will go ahead and analyze how it have to grab the results from the database file system. That's all it does. Once the query is sent to the transaction manager component, the transaction manager component has two subcomponents in it, the log manager and log manager in it. So for the read transaction, we are not making any modification to the database pages. So the transaction manager will go ahead and just invoke log manager part of it. It will go ahead and request the buffer manager to put a shared log on the resources that the buffer manager needs. Now, why shared log is because this is just a read transaction and not the write transaction. We do not want to block any other queries that are running simultaneously. So once the query has reached the buffer manager component, the buffer manager component will first go ahead and put a shared log on the resources that it needs, and then it will go ahead and check if all of the resources that it needs to process this particular query are already in the buffer pool, or if it have to go ahead and grab any of the pages from the disk file system. If it didn't find any in the buffer pool, it will go ahead and grab those pages in the form of 8 KB pages, put them in the buffer pool, do the operation over there, and send the results to the user. The read transaction is very simple. But what happens with the write transaction? The access methods by itself, it doesn't perform any action, but all it does is to analyze how it have to grab the results from the database files. Once the query is sent to the transaction manager component, the difference happens here. Now, as it's the write transaction, before writing anything into the database pages in the buffer pool, first the transaction manager should invoke the transaction log part of it, transaction log manager part of it, and then it have to first write what all operation it wanted to do, what all modification it wanted to do in the transaction log first, and then it will invoke the log manager part of it. It will request the buffer manager to put an exclusive log on the resources that the buffer manager needs. Now, why exclusive log is because it's a write transaction. We do not want other users to be interfering with our transaction, right? So once the query has reached the buffer manager component, the buffer manager will first put the exclusive log on the resources it needs to process the query. And then it will go ahead and check if those pages are already existed in the buffer pool. If it didn't find some of them or any of them, it will go ahead and grab those pages in the form of 8 KB pages, just like the read transaction, put them in the buffer pool, do the modification over there, and send the results to the user saying it is successfully completed. But did you observe the database page, the data pages, the 8 KB pages are already written in the buffer pool here, but they are not hardened yet to the disk file system, right? That's when the checkpoint process will be kicked in to grab these dirty pages from the buffer pool, push these dirty pages back into the database file system, and harden them onto the disk. That's how the checkpoint process works, and that's how the write transactions work behind the scenes. Now let's see a very quick demo of how these pre-optimization stages work. The first step inside the relational engine, the parser, binder, simplification, and the trivial plan. Let's see how those work inside our management studio. Michael, can you please confirm if you are able to see my management studio?
Sorry, yes.
Thank you. So in this particular demo, I'm using AdventureWorks 2016 database. Let me put that database in the context. And let me first show you how the parser works. To enable the parser, we can just set the parse only option on, or also we can just do the parse by using this particular button in the management studio. Let me turn on the set parse only option on. Now, when I turn this option on, only the parser component will be invoked. Now, let me do a very simple select statement, which doesn't have any syntactical errors, so it should not throw me any error here. Now, let me show you a very simple select query where it is using the variable, but we are not actually declaring the variable, but we are using the variable in the where clause. Now, when I execute that, it should throw me an error saying must declare the scalar variable. That's how the parser works. And let me do a select statement, like select non-existing column from a non-existing table. Now this column and table is not existed on this particular database. Now let's see if it will go ahead and identify. No, it doesn't, because there is no syntactical error, right? The objects are not valid, right? So these objects are validated at the binder component, not at the parser component. The parser, all it does is it will just validate the syntax and it will check and validate the variables. Now let me turn off this parse only option off. And let me turn on set format only option on. Now this format only option on is not used these days, but is deprecated. But still, for this demo, I wanted to clearly show how the parser and binder works behind the scenes. So let me turn off this parser set format only option on. When I turn this option on, the parser as well as the binder components will be invoked. Now here we have a very simple select statement. All the objects and the tables are the columns as well as the tables which we are using in this select statement are valid. So when I execute it, it should not throw me an error. And when I turn on this format only option on, it doesn't generate an execution plan or it doesn't execute the results. It will just invoke the parser and binder part of it. Now let me run that particular select non-existing column from non-existing table this time, and let's see if this will throw an error. It should throw an error, right? The binder part of it got invoked right now. Let me turn off this format only option off. And let's see how the data type resolution happens at this binder component. Now, we have a simple select statement between two tables, and the ordinal column of those two tables should be matching their data types, right? The customer ID is of integer data type and sales order ID is also of integer data type. Now, when I execute this, it doesn't, it should run the query properly, right? It doesn't throw an error. But here I manually created a data type resolution error by saying customer ID is of an integer data type here, and the credit card approval code is of varchar data type. Now, when I execute this particular query, it should throw me a conversion failed error. Now that's how the parser and binder works. Now let's see how the simplification works. Now for this demo also, let me put the database in the context, the same database, AdventureWorks 2016. And at the simplification phase, the simplification should go ahead and simplify the query, right? Here we have a very simple subquery in it. Let me turn on the actual execution plan on. And when I execute this particular query and see the execution plan, it should just go ahead and do a very simple inner join. That means it actually went ahead and it converted that particular subquery into a simple join behind the scenes. Let me do here at the simplification phase. The simplification will also remove any redundant joins. That means we are just grabbing the results here from just the sales order header table, but we are using the customer table here without any use. We are not grabbing any results from the customer table. So let's see if the SQL Server will go ahead and remove this redundant joins. When I execute this query and see the execution plan, it will grab the results just from the sales order header table. It doesn't use the customer table at all. Now let's see how the contradictions are handled. Now here I manually created a contradiction error saying where territory ID is equal to 1 and where territory ID is not equal to 1. Now when I execute this particular query, it should not throw me any results. It will also doesn't throw an error. You know why? Because this is at the pre-optimization stage and the SQL optimizer doesn't know what values we are using at the pre-optimization stage. So even if we use the territory ID is equal to 100 and territory ID is not equal to 1, it doesn't know what values we are using. So that's the reason it didn't throw an error, but at the same time, it doesn't show any results, obviously. Now let's see how the trivial plans are generated. Now this is a very simple query, right? How SQL Server will think this query, whether it generates full plan or trivial plan. Let's see. When I execute this particular query and go to the execution plan and do undo the properties on the select and see the optimization level here, it chooses the trivial plan. That means this particular query is treated very simple by the SQL Server because it's a very simple select query with a where clause. Now the SQL Server thought this is a very simple query. It wanted to create the trivial plan no matter how many times the user runs the same query. The SQL Server will go ahead and create those trivial plans on the fly those many times. And these trivial plans by default are not saved inside our plan cache because the SQL Server wanted to save that particular memory inside the cache for more complicated queries. Now let's see, but there are some scenarios, right? Whenever you don't expect the SQL Server to create the trivial plan sometimes, but it will go ahead and create the trivial plan, and you do not want that. You want to save that particular plan, which should be the full plan. You are expecting a full plan, and you want to save that full plan inside your plan cache. Now, in that particular scenarios, there is an option to turn on the trace flag 8757 to that particular query where you want to convert that trivial plan into the full plan. Now, whenever you use that particular trivial plan in that particular query, it doesn't affect the database level or the server level. It is bound to that particular query only. So I do not recommend this to do in the production, but there are always chances, right? You wanted to save those plans. Whenever you wanted to do that, you can turn on this trace flag 8757. So when I execute that and then check the execution plan, the same query with the trace flag on, when I go to the properties and see the optimization level, that particular trivial plan is now converted into the full plan by using the trace flag 8757 turned on. Now that's how the trivial plan component works. Now let me hop back into my slides very quickly. And this is my summary slide, like what we have gone through in this session today. We have gone through the overview of ACID properties of transaction with a simple example ensuring the ACID properties. We have also gone through the overview of different types of components we have in the memory architecture of SQL Server. We have gone in deep into the major components, how the plan cache and the buffer pool gets managed inside the SQL Server. And we have seen the life cycle of a query for the read as well as the write transaction, like what happens behind the scenes at each component inside the relational engine as well as the storage engine. And we have seen all the different types of components we have both in the relational engine as well as the storage engine. These are the resources that I used to prepare for my presentation. And mostly I followed the Kevin Klein and the Pro SQL Server internals written by Dimitri. If you wanted to go in deep into the SQL Server internals and architecture, please follow these resources. And I have that 8 kV resources too on my slide. A very big thank you for giving me this wonderful opportunity to present for your GLASS user group. And thank you so much, Michael, for giving me this wonderful opportunity. And at this situation, if you have any questions, please do not hesitate to ask me.
Yeah, thank you very much.